Greetings everyone, my name is Dinan and today I will be presenting our research on comparison of ballistic performance of 4340 steel, aluminum 7075 T6 and aluminum 6061 with aluminum oxide composite against 7.62 mm bullet impact with numerical approach. The main challenge in designing modern tactical vehicles is finding armor that is both strong and lightweight. For a long time, 4340 steel has been standard for protection because it's very strong and tough. However, it is also very heavy. This has led us to explore lighter materials. The first lightweight material is aluminum 7075 T6, a superior aluminum alloy known for its high strength. The second material is an engineered material, an aluminum 6061 reinforced with aluminum oxide. Here we take a common aluminum alloy and reinforce it with hard ceramic particles to improve its performance. This leads to our research question. How does the performance of these lightweight materials compare to the ballistic resistance of 4340 steel with the same volume each material? Simulation is the answer. We use numerical simulation with finite element analysis software. So for our geometric model, we use 7.62 mm mild steel projectile. The targets were 100 by 100 mm plates, and importantly, all targets had a uniform thickness of 15 mm. This allows us to test the absolute performance of each material within the same volume. For the material models, we used the Johnson-Cook model for the composite, while the data for the other materials were taken from the software library. The parameters for this model were validated using the data from the literature from Hilfe and Brar in 1996 for the aluminum 6061 with 15% aluminum oxide. The simulation was set up with an impact velocity of 732 meters per second, and all target plates were fixed on all four sides. All materials were designated as flexible, which allowed the projectile and target plate to deform upon impact. And here is the Johnson model we obtained from Hilfe and Brar. We manually added the data since the data for our composite material is not available in software library. So now for our main results, the key finding is that all of our primary targets successfully stopped the projectile since there was no penetration, there was no perforation as well. Our main metric for performance is the back face signature, or we can call it BFS, which is the deformation on the back of the plate. A small BFS means better performance. As you can see from the table below, 4340 steel is the top performer with a very small BFS of only 0.16 mm. Among the lightweight options, aluminum 7075 T6 performs very well with a BFS of only 0.86 mm. And now for the aluminum 6061 composite comes next with a BFS of 2.07 mm. For comparison, the standard aluminum 6061 base alloy had largest deformation at 3.25 mm. By adding ceramic particles to the standard aluminum 6061 alloy, we achieved a 36.9% improvement in performance, reducing the back face deformation significantly. Okay, so now we take a look at the image. The stress distribution in the 4340 steel plate is characteristic of a very hard and tough material. The simulation shows that the high stress zone is highly concentrated in a tight, bolt-like shape directly beneath the projectile. This indicates that materials high strength resist the projectile in localized area, efficiently absorbing the impact energy without significant damage propagation. In aluminum 7075 T6 alloy plate, the high stress zone is noticeably larger and more spread out compared more conical shape through the plate's thickness. This behavior is characteristic of a high strength yet more ductile material. This widespread distribution of stress and energy allows it to perform well, but it also results in a slightly deeper crater and larger backface signature than the steel. The stress distribution in the aluminum 6061 with the 15% aluminum oxide reinforcement highlight its less efficient combination of brittle and ductile behavior. A concentrated high-stress region forms just beneath the impact point, indicating the initial resistance offered by the hard aluminum oxide particles. However, when compared to the base metal, aluminum 6061, it demonstrated a typical ductile response. The stress is spread wider and has larger area. It is not capable of resisting impact forces locally. And next we have the data we get from the simulation tests. Here are the shear stress data experienced by each target material to understand damage mechanism and material resistance of projectile penetration. There are two shear stress data that we took in the XY plane. On the graphic is marked with the blue line and YZ is marked with the red line. Shear stress analysis shows that 4340 steel has the highest resistance to frontal impact, indicated by the largest shear stress value in YZ plane with 347.4 megapascal. Next, followed by the aluminum 7075 T6 performed moderately, while the 6061 with 15% aluminum oxide and best alloy showed significantly lower shear resistance, indicating a higher risk of damage when exposed to projectile penetration. Overall, the higher the shear stress value in the YZ plane, the better material's resistance to bullet penetration from the x-axis direction. The conclusion is for armor designs with limited thickness, 4340 steel remains the material with the highest ballistic performance. Aluminum 7075 T6 is the most effective lightweight alternative in this scenario, offering the best balance of strength and ductility in a monolithic alloy. Engineering a composite from aluminum 6061 is a valid and effective strategy for significantly improving its ballistic performance. The addition of hard aluminum oxide particles reduces the ductility of the matrix, causing the material to fail locally rather than absorbing energy through extensive plastic deformation. However, it is important to note that addition of 15% aluminum oxide significantly improves the ballistic performance of the base aluminum 6061 alloy, reducing the BFS from 3.25 mm to 2.07 mm. This proves that composite engineering is a valid approach to improving the capabilities of the base material. So thank you for your attention. I would now be happy to answer any question you may have.